Our final tutorial lecture for today will be presented by Professor Kendric Smith from the United States. Professor Smith will be introduced by Chairperson Professor Masayoshi Okada.
She lectures were beautifully. She lectures beautifully.
Now let's begin. Ladies and gentlemen, start the tutorial number 5. His title is Laser and LED Photobiology, presented by Professor Emeritus Kendric Charles Smith. And he was born in the October 13th, 1926, in Illinois, United States. He became a professor of the Department of Radiology, Stanford University. Thereafter, emeritus, 1993. Thereafter, he has continued his activity on the laser works. He belonged to the many kind of the society in American and European countries, and numerous number of the scientific papers published in the world. So could you start with your lecture, please, Dr. Smith?
Thank you.
Yeah.
Thank you very much. I'm very pleased to have been invited to this important symposium. Low-level light therapy, or LLLT, is a very important, relatively new area of photomedicine. However, there are a number of reasons why LLLT has not been accepted into the mainstream of science and medicine, and I will discuss a few of them today. Let me add, however, that I know firsthand from personal experience that LLLT works on wound healing and carpal tunnel syndrome when done properly. See, I need to press the button here. I've been trying for over 40 years to teach photobiology to laser people, and more recently to LED people as well. At a laser meeting in the 1970s, at the height of the feeling that lasers were magical, I made a slide to demonstrate the biological effects of a laser. This one. It showed a man dropping a laser on his foot and yelling, "Ouch." I said, this is the only type of biological effect that a laser can have on a person. It is the light that's produced by the laser that has the biological effect. A laser is just an expensive flashlight, and it is the light produced by the laser that has a chance of producing the biological effect, assuming that it is of the correct wavelength and of the proper output. Well, I'm still trying to educate laser and LED people about photobiology, and at this meeting I'll probably be preaching to the choir, but just in case someone in the audience doesn't really understand the first law of photochemistry, here goes. There are two main reasons for bad papers on LLLT. One is the lack of proper scientific training by the authors, and the other is their lack of knowledge of photobiology. I will give you some examples of bad science. At an LLLT Congress some years ago, the speaker proclaimed that LLLT was effective in reducing high blood pressure. In the so-called clinical trial, the patient came in and his blood pressure was taken, and then his neck was irradiated with a laser of whose wavelength I do not remember. Then they measured the patient's blood pressure again, and lo and behold, the blood pressure was lower. Was this another magical effect of lasers? No. I asked the speaker if he'd also tested the blood pressure 30 minutes after the laser treatment, or after 1 hour, or after 2 hours, and he said no. Then I told him my story. While preparing for my trip to that Congress, I was rushing about the drugstore picking up toothpaste and so forth, and I saw a new blood pressure machine there, and I sat down to take my blood pressure. My blood pressure was way above normal. After a few moments of sitting and reading the signs on the machine, I decided to test my blood pressure again. And lo and behold, it was normal, even without laser treatment. Sitting down in a chair for a few moments worked magic. The problems mentioned for this blood pressure experiment are by no means exceptional. Numerous papers in the literature report that an experiment was carried out for a certain period of time, and with each irradiation was improvement. What would happen if the treatments were carried out longer? What would be the beneficial response? Would the beneficial response continue, or would it reverse and become detrimental after further irradiation? What about checking the patient a week later? Would the results still be positive, or was the treatment therapy only temporary? Here's another example of bad science and bad photobiology from a paper by Rosner et al. On delaying optic nerve degeneration by low energy laser irradiation. The authors used non-coherent 904 nanometer radiation and coherent 633 nanometer radiation. They reported that the non-coherent radiation adversely affected the nerves, while the coherent light was very effective. They then concluded that this proved that coherence was important in LLLT. Unfortunately, the paper proves nothing about coherence. In the first place, you can't run a proper scientific experiment when you vary two important variables, wavelength and coherence. They varied the wavelength, but they did not understand photochemistry, and they varied coherence, and they did not understand physics. Nothing was mentioned about heat during the treatment of the optic nerve, so we don't know if the authors made sure that they were not cooking the nerve with the LED irradiation, and that's why it was not effective. The authors also point out that the energy of the two different sources of radiation was markedly different. Could this have been another reason why 904 nanometers was less effective? Also, the light treatment only delayed the death of the nerve. It did not reverse the damage. So what was the point of this publication? It is not a success story for LLLT. It was bad science. The paper should not have been published. Unfortunately, this paper was cited in the Laser Therapy Handbook by Tuner and Hode as proving that coherence is very important in LLLT. Enwameka et al. Have published 2 papers about controlling infections of methicillin-resistant Staph aureus with blue light. This is certainly of importance. But in each paper, these authors proclaim with wonderment that the survival curves were not linear. The people who enter a new field, such as radiation biology, they should do their homework. Radiation biologists have been producing survival curves for many decades. And of course, radiation survival curves are not linear. And no radiation biologist would plot the data on linear graph paper. They use semi-log plots because these plots provide a lot of information about the organism being studied. Here's a survival curve that came from the paper radiation of Staph aureus. All you can tell from this curve is that cells were killed. But look, they only went down to 10% survival. If you take those same data and plot them on semi-log paper, you can get information about what's going on. you will immediately see that 30% of the cells are much more sensitive than the remaining 70% of the cells, and both have one-hit kinetics. But why are the two populations of cells so markedly different in their sensitivity to blue light? Since the authors do not mention how the bacteria were grown, we do not know if part of the cells were in a different phase of the cell cycle, for example, in stationary phase, and this might be why their radiation sensitivities were different. Alternatively, the culture could have been contaminated by two closely related strains with different radiation sensitivity. Without a proper description by the authors who performed the experiments of how they performed the experiments, we'll never know the answer. Here is more information about this paper from a letter to the editor. Phototherapy miracles in a nutshell. To the editor, the fact that light used in phototherapy can perform miracles was recently impressively demonstrated by Nwameka by killing methicillin-resistant Staph aureus in 24 hours with intensive blue light. One can imagine which editor of this journal accepted this letter. If you don't know, it's Nwameka. The Nwameka paper does not describe a miracle in phototherapy. It is a bad paper on radiation biology. The authors only killed the cells to 10% survival. This is not enough killing to cure an infection. One would need to kill to at least 100%, and maybe that is not enough. If you extrapolate these data from their curve to 0.001%, if you take their original data at 10% and extrapolate it to 0.01%, you see that you need 185 joules per square centimeter of 470 nanometer light to kill these cells. What would be the consequence in tissue if with this very, very high dose of blue light? Would the cure be worse than the infection? I'm pointing out these examples because I hope that they will stimulate people to write better papers and to do a better job of reviewing and editing papers. To continue the lecture on radiation biology, the curve on the right, where's the red light here, is a typical curve for a radiation-resistant bacteria with its shoulder. So it means that it requires a lot of energy put into the bacteria before they lose their capacity to repair the damage and finally end up in a single-hit kinetics. The middle curve is typical of a radiation-sensitive mutant of the more resistant strain. You see it doesn't have the capacity to repair, so there's no shoulder on the survival curve. Radiation biologists also quantitate information derived from these curves, and you can see some of them on these thing. You report the slope of the survival curve, the place where it intersects the 100% survival, called the DQ, and when it intersects the zero dose line. And these are important for tabulating and comparing curves without necessarily having the curves in front of you. Clearly, the absence of scientific training is a big factor in the production of bad papers on LLLT. I don't want to put all of the blame on the authors for bad papers. I must also include bad reviewers and bad editors, and unfortunately, there are a lot of these. Fortunately, there are only a few basic laws of photobiology, but if researchers and clinicians do not know them, then their studies will be worthless, and they will mislead other people who are similarly untrained. Again, I have to put some of the blame on bad reviewers and bad editors.